Lesson 313. Today we're going to work on solving nonlinear systems of equations. So you've spent a lot of time in algebra and geometry and algebra 2 solving systems of equations. And hopefully you've worked through methods of substitution, or elimination, or graphing. We can continue to use these methods for all systems of equations. So for example, if I'm going to solve this system for x and y, I can pick any method that I would like. I'm going to choose substitution. So first I'm going to work to get one of the variables all by itself in one of the equations. So subtract 3x from each side to get that y by itself. I can then take that value of y and plug it into the other equation. Don't forget to distribute the negative sign, so you have a negative 20. Combining like terms and adding 20 to each side, x is equal to 1. So if I know that x is equal to 1, I can take that value and substitute it into my original equation to get y equals 2. One of your homework problems from an earlier section asked about the graphs of these two equations. Looking at this first equation, you have a quadratic. The second equation is a line. So if you think about how a quadratic and a line intersect, they could either intersect nowhere, or they could intersect in one location, or they could intersect in two locations. So if I'm going to work to figure out where they intersect, I could graph them, I could use substitution, or I could use elimination. Since I already have a variable all by itself, I'm going to use substitution. So I'm going to take the 2x minus 1 and substitute for y in the first equation. Again, don't forget to distribute the negative sign to both terms in the parentheses. Solving a quadratic, I need to make sure that all terms are on one side and my equation is set equal to 0. I can factor that quadratic. And I end up with a solution of x equals 3 and x equals negative 1. So there are going to be two solutions to this problem. So I know that I'm dealing with this situation. The line is hitting that parabola in two places. So if x is equal to 1, I substitute negative 1 in for x. And I get y is equal to negative 3. If x is equal to 3, I get 5. So when I'm writing my final answer as ordered pairs, this line hits that parabola, and one of the locations, x is negative 1 and y is negative 3, and the other location on the graph, x is 3 and y is 5. So you're going to write your solutions as ordered pairs, because what we're really talking about is where those equations intersect on a graph. So if I'm going to try and predict how many solutions I have for these systems, I have to look at the equations and determine what kind of equations they are. This first equation is a line, and my second equation is a line. So if I think about how two lines can intersect, those lines can be parallel, which means there would be no solutions or no intersection points. Those lines could cross each other in one location. Therefore, there would be one solution. Or those lines could be on top of each other, which would give me infinite solutions. Looking at my second problem, letter B, I have a quadratic in the first equation because the y is squared, so it's a quadratic on its side. And I have a quadratic in the second equation because the x is squared. So I have a quadratic that opens up. So again, thinking about how these two shapes could intersect each other, I could have 4 solutions. If it looked like that. I could have 3 solutions if the graphs intersected like this. And then hit at 3 points. I could have 2 solutions if the graphs intersected in only 2 spots. I could have 1 solution if the vertex of the second graph just touched in 1 spot. And I could have no solutions if those graphs did not intersect at all. Continuing on and thinking about how many solutions these systems would have, my first equation has 3 roots. So this is a cubic equation. My second equation is a square root equation. So if I think about a cubic equation and a square root equation, my square root equation could hit that graph in 3 points. Or I could have a square root that only intersected that graph in 2 locations. I could have a square root function that only intersected the graph in 1 place. Or I could have a square root function that did not intersect that graph at all and have 0 solutions. And lastly, in problem D, since I have x and y multiplied together, I know that I have a rational function. In the second equation, I also have a rational function. So remember, a rational function has two pieces separated by asymptotes. So if I think about how those would intersect each other, I could also either have 4, 3, 2, 1, or 0 solutions. So I've given you the graphs of these equations so you can see how they look on a coordinate plane and the solutions that you would get. So if I look back at these systems of equations and think about which ones I would like to solve algebraically. So which ones are going to be easiest to either eliminate a variable or solve for a variable? Letter A is 2 lines, so that doesn't seem too bad. Letter B is 2 quadratics. Those are not bad. I could probably work on solving those algebraically. C and D are definitely more complex fraction or more complex equations. So they would definitely take a lot more time to solve algebraically. I would probably try these graphically using my calculator or using Desmos. So if I'm going to work to solve this system of equations algebraically, I have to think about using substitution or using elimination. I like to try and eliminate a quadratic variable. So while I could take the y and plug that into the first equation, I'm going to actually rearrange that second equation to get the x squared by itself. Because then I can take y plus 14 and put that in for the x squared. So I end up with the equation y plus 14 plus y squared equals 34. So now I have a quadratic that I need to solve. So I need to move everything over to one side of my equation. Factoring that quadratic, I have y plus 5 and y minus 4. So solving for y is negative 4, or y is 4. So remember, I need to write my solutions as ordered pairs, because what I'm really trying to figure out is where this line intersects this circle. So I need to plug my values for y back into one of the equations. So if y is equal to negative 5, x squared is equal to 9. So x is equal to plus or minus 3. So if I start to write out my solutions, when x is 3, y is negative 5. If x is negative 3, y is also going to be negative 5. Now I'll work with my y equals 4. So plugging 4 into that equation, x squared is equal to 18. So x is equal to plus or minus the square root of 18. Simplifying that radical, I have x is equal to plus or minus 3 times the square root of 2. So writing out my ordered pairs, if x is a positive 3 times the square root of 2, y is 4, and x is negative 3 square root of 2 when y is 4. So oh, I'm sorry, this was not a line. Because we have 4 solutions. So this is a quadratic. So if you think about a quadratic intersecting a circle, that quadratic is hitting that circle in 4 different places. So I have 4 solutions to this problem. Continuing to solve these systems of inequalities, or systems of equations, again, you have to think about either substitution or elimination. So we've got lots of options for each of these problems. I would start this first one by getting the x all by itself. So x is equal to 6 divided by y. So if I plug that into my second equation, I have 36y squared plus y squared equals 15. To get rid of the denominator, I'm going to multiply both sides of the equation by y squared. So I have 36y squared plus y to the 4th. I'm sorry, 36, because the y squareds cancel each other out. So I have 36 plus y to the 4th equals 15y squared. Moving the 15y squared over, I can factor this to be y squared minus 12 and y squared minus 3. So y squared is equal to 12 and y squared is equal to 3. So y is equal to plus or minus the square root of 12, or y is equal to plus or minus the square root of 3. Simplifying my radical, y is equal to plus or minus 2 times the square root of 3. So I'm going to have lots of solutions to this problem because I need to plug positive 2 square root of 3 in for y, negative 2 square root of 3 in for y, positive square root of 3 in for y, and negative square root of 3 in for y. So if I start with the positive 2 times the square root of 3, six divided by 2 is 3. Rationalizing the denominator, x is the square root of 3. So starting to list out my solutions, x is the square root of 3 when y is a positive 2 square root of 3. Putting in a negative 2 square root of 3 for y is going to give me a negative square root 3 for x. So I have my second solution. Putting in a positive square root of 3 for the y. I get 2 times the square root of 3. So x is 2 square root of 3 when y is a positive square root of 3. And lastly, putting in a negative square root of 3 for y, I will be left with a negative 2 square root of 3. So again, I have 4 solutions to that system of equations. Let's try one more. I've got negative exponents, rational exponents. Kind of looks like a mess. I'm going to use elimination to solve this problem. So I'm going to start by multiplying the top equation by 2. And I'm going to leave the bottom of the equation alone. So if I add these lines together using elimination, my y terms cancel each other out. So I'm left with 7x equals 7 and x equals 1. So if x is equal to 1, y is equal to, I'm going to subtract 2 from each side. So y to the negative 5/2 power is equal to 4. To get the y by itself, I'm going to raise each side to the negative 2/5 power. So y is equal to 4 to the negative 2/5 power. So my solution is the ordered pair 1, 4 to the negative 2/5 power. So for each one of these problems, when you're solving algebraically, you're going to solve for x or y, and then substitute that value back in to find how many solutions you have. So I've listed out the solutions and the work for each of these problems, so you can take your time going through them. Please bring any questions to class or send me an email. And homework problems I would like you to focus on for this section are listed, and please turn these into Canvas.